So good evening everyone. Welcome to the online NPTEL certification course on the topic water and wastewater treatment. So we'll start with week 11 lectures. Okay, so the contents of week 11 we will see, and then we will solve some multiple choice questions. So as you all know, the course instructor is Dr. Bhanu Prakash from IIT Roorkee, and I am one of the teaching assistant. My name is Akash Shah, and I am a PMRF scholar at the Department of Civil Engineering at IIT Madras, where I am pursuing my PhD in environmental engineering. So we'll see the contents of week 11 now. So as you all know, we started with the concept of adsorption. What is adsorption, and what are its various mechanisms, and how activated carbon helps in absorption, and what is its process. Then we talked about granular activated carbon breakthrough, and then moved on to the topics of absorption isotherms, where we learned about various models like the Langmuir, Freundlich, and the BET isotherms. Okay, so that was about absorption. And then we started discussing regarding the ion exchange methods. What are the various types of ion exchangers, and how does the selectivity matters in ion exchange processes. And after that, we moved on to filtration processes, where we talked about nanofiltration and reverse osmosis. What are the various parameters and the properties. And at last, we saw the concept of aeration for the removal of ferrous and manganese. So that's what about the contents of week 11. Okay, so we will see some multiple choice questions, and then we will discuss some subjective problems also. So starting with the first question, uh, the first question says that calculate the water recovery in percentage for the following RO process data. Okay, so here we have been given the permeate flow, that is around 200 meter cube per hour, the feed flow, that is around 250 meter cube per hour, and the flux considered it's 18 liters per meter square per hour. So we have to calculate the we have to calculate the water recovery. So I'll wait for some time for you to solve, then I'll give the solution. So let's see the solution. So this is question number one. So generally a membrane, we will represent it as like this. So this is just the schematic. So this is the feed, and then from here we will get the permeate. So it is showing that the feed flow is around 250, whereas the permeate is around 200. So the units can be meter cube per day, per hour, whatever. So so in the question the unit is given as meter cube per hour. Okay, so this is meter cube per hour, meter cube per hour. Okay, so we are asked about the water recovery. So this is nothing but the ratio of the permeate flow by feed flow. So per feed flow, how much permeate we are getting. So that's what gives the water recovery ratio. So it will be nothing but 200 divided by 250, that is equal to 80%. Okay, so that's how we have to define the water recovery. One more term that is uh, quite often asked in these questions is the rejection ratio. Rejection ratio. So suppose the inlet, the feed that is coming is having a concentration of CF, and the permeate is having a concentration of Cp. So we define rejection ratio as 1 minus Cp by Cf into 100. So this is how we define the rejection ratio, like how much rejection of the uh, contaminant or the pollutant is happening through the membrane. So these are the two basic parameters which we generally come across membrane filtration. So in membrane filtration, there are various types. We can see it can be a microfiltration, it can be an ultrafiltration, it can be a nanofiltration, or it can be a reverse osmosis. So we have seen and talked about all of these, and these are the two basic parameters, right? So 80% is the correct answer. Moving forward, the second question says that adsorption of toluene onto activated carbon obeys Freundlich isotherm equation, where C is in milligram per liter and Q is in milligram per gram, given below. The concentration or the adsorption capacity Q toluene is given as per the equation of 73.4 into concentration of toluene to the power 0.365. So that's how the isotherm has been defined. Now it says that a solution at 25 degrees Celsius containing 0.85 milligram per liter of toluene is to be treated in a batch process to reduce the concentration to less than 0.03 milligram per liter. So we are required to calculate the dose of activated carbon. So it is asking the required activated carbon dose in milligram per liter rounded to one decimal is. Okay, so it's just a batch experiment where the toluene is being adsorbed on the activated carbon and it is following the Freundlich isotherm. The equation is already given and the initial concentration is given as 0.85 milligram per liter and the final concentration uh, to be reduced it till is still 0.03 milligram per liter. Okay, so go through the question once again and try to solve. I'll wait for some time for you to solve and then I will get back with the solution. So coming back to the solution. So this is question number 2. So here, if you I want to explain the process. So what is happening? Suppose there is a reactor. Okay. So inside there is some toluene and the initial concentration is around 0.85 milligram per liter. Now you have added some activated carbon, okay, at the absorbent. So some activated carbon has been added. Okay, so now when the when the process start, the toluene will be getting absorbed on the activated carbon and the final concentration. So this is the initial concentration and the final concentration is around 0.03 milligram per liter. So you are being asked how much of this activated carbon dose. So you have to find out the dose. What is the dose? Okay. So if you see the isotherm, so it will follow a particular isotherm equation. So here it is defined by the Freundlich isotherm. So it is given as Q toluene is equal to 73.4 into C 0.365 toluene. Okay, so this will be around 73.4 into 0.03 to the power 365.365, right? So if you solve this, so this will be my, this is nothing but the final, what is the final concentration, that only we have to put. So in that way the absorption capacity we will get as milligram per gram. Okay, so this is the capacity. Now we will apply the mass balance. So applying mass balance on the contaminant, that is toluene, to get activated carbon dose. Okay, so as per mass balance, the mass before and initially whatever was the mass, that should be equal to the leftover mass plus whatever mass is absorbed on the activated carbon. Okay, so this is, suppose the total toluene that was present initially, this will be equal to the concentration of toluene remaining in the system now plus whatever is absorbed. So by absorbed we can define it as the absorption capacity of toluene into the concentration of activated carbon. Okay, into the concentration of activated carbon. So initially it was 0.85 and finally it was 0.03 plus the absorption capacity 20.41 into the concentration of carbon. So if you solve this, you will get it as 0.0401 gram per liter, or we can say the dosage of activated carbon required is 40.1 milligram per liter. So this is how you have to solve the problem. So first take whatever the isotherm equation is given. Okay, calculate the absorption capacity. Okay, then apply the mass balance. So initial some amount of toluene was there, that should be equal to the final amount and some part which is absorbed by the activated carbon. So three aspects are there. So just equate them in an equation and then calculate the dosage of carbon. So that's how you have to do. Okay. Okay, moving forward. So it says that match the following isotherms with their respective descriptions. So we have four different isotherms. One is the Langmuir isotherm, linear isotherm, Freundlich isotherm, and the BET isotherm. So BET, nothing, it means it's a name of three scientists, Bronner, Emmett, and Teller. And the respective descriptions are given. You have to match with the particular isotherm. Okay, so just go through the question once again and try to come up with an answer. So four options are being given with different matches. You have to tell me the correct answer. Okay, I hope you have decided on the answer. So let's see the correct answer. So the correct answer is B. Okay, so if we see B, so first the if we start with the Langmuir isotherm, so it is generally assumed in a Langmuir isotherm that only one layer or mono layer of adsorption will be happening. Okay, so Langmuir always assume that only one layer of or mono layer adsorption will happen. Then linear isotherm. So as the term says, it is linearly dependent on the concentration of compound. So whatever the solid phase concentration is, it is linearly dependent on the concentration of compound in water. Okay, so that's why since there is a linear dependency, it is called a linear isotherm, as the name suggests. Then the third is the Freundlich isotherm. So the Freundlich isotherm is generally used for a fit for the granular activated adsorption. So as we saw in the previous question, so in the same question regarding the activated carbon adsorption, we have been given a Freundlich isotherm. Okay, so it's most of the time it is the better fitting isotherm. And the last one is the BET isotherm. So this BET isotherm is generally utilized when we are assuming that there are several layers of adsorption. Okay, not monolayer but multi-layer adsorption is there. So for monolayer we will generally go for the Langmuir isotherm, whereas for multi-layer we will go for the BET isotherm. Right? So I think that's it to discuss about this isotherm. Next question. Select the correct statements regarding reverse osmosis theory. So here we are to discuss about the reverse osmosis theory. First, it says that chemical scale fouling in membranes occurs due to the increased concentration of ions in concentrate. Solute rejection is lower for highly charged molecules but higher for larger molecules. Uh, Membrane material is susceptible to biological degradation and degrades with free chlorine concentration below 1 milligram per liter. And at last, volumetric flux of water is given by JW is equal to KW into delta P minus delta pi. So we have four statements there. So just go through the statements, try to understand how is it related to, they are all related to the reverse osmosis theory. Just think whether it's wrong or right, and if it is incorrect, also try to understand that what would be the correct way of representing the statement. Okay, so the correct answers are A and D. So definitely chemical scale fouling will occur on the membranes due to the concentration of increased concentration in the concentrate, and also the volumetric flux equation that has been given is correct, so there is no doubt about it. Whereas if we see option B and D, so when we are talking about highly charged molecules like sulfates, for example, they are typically rejected more effectively by reverse osmosis. Okay, and this is due to the electrostatic repulsion and the Donan dialysis effect, where the charged membranes repels the similarly charged ions. Okay, so the rejection will be more for highly charged molecules, not less. That's why B option is incorrect. And also the membrane material is susceptible mainly to membrane fouling, not to the biological degradation. In general, it is not susceptible to the degradation, but to the biological fouling. Okay, so any kind of polymeric membrane or polyamide, this type of membranes, the fouling will be a major problem. Okay, but not the degradation in a stricter sense. So that's what I wanted to discuss regarding the fourth question. Moving forward, what does sequestration mean in reference to ferrous and uh, manganese removal? So is it nitrates are added to the water to bind the ferrous and manganese to precipitate out? Phosphates are added to water to bind the ferrous and manganese to make soluble in water. Phosphates are added to water to bind the ferrous and manganese to precipitate out, or the process of formation of aqueous complexes of ferrous with NOM, that is the natural organic matter. So, what do you mean by sequestration of ferrous and manganese removal? Just think about it. Okay, so the major concern will be in, I think, in option B and C, whether the phosphates are added to make it soluble in water or to make it precipitate out. So generally sequestration means that the phosphates are added to bind the ferrous and manganese ions to make them more soluble in water. Okay, to make them soluble. So why it is done? So in the context of iron and manganese removal from water, sequestration refers to the use of chemicals. So generally we will add polyphosphates or sodium silicate to bind this ferrous and manganese in soluble form, so that we prevent them from oxidizing, okay, or we prevent them for precipitating. So both the things are prevented, which can cause staining and other problems. Okay, so we don't want them to get oxidized in the soluble form, or we don't want to let it precipitate. Okay, but we want them to be captured or to be bind with the polyphosphates. So that's what is meant by sequestration related to the context of ferrous and manganese. We have also, in generally, we see this sequestration term with respect to carbon. We call it as carbon sequestration. Okay, so similarly, here we are talking about iron and manganese sequestration, right? Now, moving forward, we have the sixth question. It says that the oxidized form of ferric and Mn4 manganese are highly soluble in water. Chemical oxidation is not effective for the removal of ferrous because it forms aqueous complexes with natural organic matter. Green sand can said to behave as an ion exchanger to remove the ferric and manganese ions. At neutral pH, Fe2 plus gets oxidized to precipitate out, but Mn2 plus does not get precipitated. So again, we are talking about ferrous and manganese removal. Okay, so just go through the statements once again and try to answer the question. Let's discuss the answer. So the correct answers are B, C, and D. Okay, so the only incorrect answer is the first statement. So because the oxidized form, that is the ferric and the Mn4 plus forms of manganese, they generally get precipitated. Okay, so these are not highly soluble in water, but kind of a precipitate. So that's what is written. The oxidized forms are poorly soluble in water at neutral pH. They tend to form insoluble hydroxides like the ferric hydroxide or manganese hydroxide, manganese dioxide. which will precipitate out. So this is regarding the removal of ferrous and manganese. Now, next question. In context of activated carbon, what does activation refers to? So does it mean heating of carbonaceous material in absence of oxygen to liberate carbon? Exposure to carbonized material to steam? Increase in surface area absorption? Chemisorption of coal and ash to surface of carbonaceous material? Or the formation of pores and fissures? So we are talking about the term activation with respect to activated carbon. Okay. So don't get confused with the process of pyrolysis, which we do to uh, form this activated carbon. Okay. Whereas activation is different. So here we are just talking about the activation. Okay, let's discuss the answer. So the correct answers are option B and option C and E, right? So because when we talk about the activation, so it generally means that it is exposed to some kind of steam, okay, and it helps in increasing the surface area of the absorption as well as the formation of more pores and fissures. Okay, so generally in the absence of oxygen, the pyrolysis will happen. That is not activation, and again the chemisorption of coal and ash doesn't really uh, induce activation. So for activation we generally do some kind of exposure to steam or increasing in the surface area or the formation of pores and fissures, right? So this was about activated carbon activation. We'll move forward to the next problem. Okay, now it is talking about the ion exchange process. So we have five statements here. You have to tell me which one are the correct statements. So the first one, it says it is easier to regenerate the weak acid resins compared to the strong acid resins. There is a stronger attraction to singly charged ions due to smaller hydrated radius. Uh, in a resin column, the exchange reactions begin to saturate the lower levels before the upper levels. HCl is used as a regenerant for cationic resins, and NaOH is used as a regenerant for anionic resins. So all these statements are regarding the ion exchange process. So you have to decide which of them are correct. You just think about it and let me know the answers if you have. Okay, let's see the answer. So the correct options are A, D, and E. So these three statements are correct. We'll see what about the other two statements, because generally uh, generally, these ion exchange resins will show strong attraction to a higher charge. Okay, higher charge and small hydrated radius. So these two are the uh, main attraction points for the ion exchange resins. So anything which has a divalent or trivalency or trivalency will get more attracted than the monovalent ions like the sodium. And also even though they have a larger radii, they will be attracted more. And whereas if we are talking about the third statement, so in ion exchange columns, the water flows from top to bottom. Okay, from the top to the bottom. So that's why the upper layers will encounter the ions first and it will get saturated first. So that's why the saturation goes from the upper layers to the lower levels instead of from the lower to the upper levels. Okay, and the other three statements are correct. So there is no problem with that. Okay, so another direct question. It says that in general, soil possesses cation exchange capacity due to the presence of negatively charged clay particles. So you have to tell me whether it's true or false. So soil also possesses some.
True.
Yes, true. Yeah, that is correct because the soil itself is having some negatively charged clay particles which will act as a cation exchange capacity. Okay. So that is true. There is nothing much to discuss. Okay, we'll go move forward to the 10th problem. So after this 10th problem, I think it's better to do some numericals, right? We will solve some numericals and then get back to the MCQs. Let's see the 10th problem first. So it says that select the correct statements regarding the chemical and physical absorption. So it says that if the pore volume is taken up by the pores of different sizes, the efficiency of adsorption is decreased. Then physical adsorption, the forces of attraction include only physical forces and exclude the covalent bonding. Then the chemical adsorption occurs. The media generally can accumulate multiple molecular layers. Then physical adsorption is an exothermic process, whereas chemisorption is an endothermic process. Then physical adsorption is generally reversible, while the chemical adsorption is generally not reversible. So you have to tell me which of the options are correct. Yes,
A D E
A,
A
D,
B E E.
E. Okay. Yeah, I think those are correct. Uh, oh, sorry, A. A is not correct because when uh, when different pores, the pore volume is taken up by different sizes. Okay, so from smaller to larger, all the pores will be filled. Okay, so the efficiency of adsorption will increase. Okay, so that's why it's a when heterogeneous kind of sizes are present, the efficiency will increase. Okay,
Okay. Okay.
yeah, and then the physical adsorption definitely it will be a physical forces will be acting and there will be no covalent bonding will be there. And then option C, generally in chemical adsorption only single layer adsorption will happen. Okay, only single layer adsorption will happen. Whereas a physical adsorption is an sorry, yeah, we are talking about option D. So physical adsorption or physisorption will have weaker van der Waals forces and can lead to multiple layers. Okay, not the chemical adsorption. And then talking about E, physical adsorption is not exothermic. The chemical absorption is mostly exothermic in nature. Okay, so B and E are the correct options, and direct and E option is correct because physical adsorption is a reversible process where chemical adsorption is not reversible. Okay, so now we'll go to some numericals. I think it is better to solve the numericals first. Question number 17, I think first. Yeah. So it says that adsorption of toluene onto an activated carbon obeys the following Freundlich isotherm equation. So that is Q toluene is equal to 73.4 into C toluene to the power 0.365, and the C is in milligram per liter and Q is in milligram per gram. So that is the absorption capacity. A sample containing 0.65 milligram per liter of toluene will be treated in a batch process to reduce the concentration less than 0.02 milligram per liter. So you are asked what is the required activated carbon dose in milligram per liter. Okay. Okay. Did you understand the problem? Is the problem clear to you, or shall I explain it? Is the problem clear to you?
Yes, sir.
Okay. Okay. If you are trying to solve it, I will wait for a minute and then I will give the solution. Did you find out the absorption capacity? What is the absorption capacity?
1 minute, sir.
Okay. Okay.
31 point something. 30, 31.
No, you are telling the final answer or the absorption capacity?
Final answer, sir. Final answer.
Final answer is around 35. Uh, okay, okay, we'll see how we are getting it. So just so for the absorption capacity, it will be Q equal to sorry 73.4 into C of C toluene, okay, to the power 0.365, right? So that
Yes.
that will be equal to 73.4 into C is 0.02 to the power 0.365. So if you solve this, you will be getting a something around 17.6024. So that's what milligram per gram
Sir, 73.4
into, yeah,
into
0.02 to the power
0.0
0.365.
the power 0.365, na?
Yeah.
Okay, okay. Yes.
Okay, are you getting 17?
Ah, yes, yes, yes. So
Yeah.
by mistakenly, I just calculated it
Yeah.
something else.
And then we have to apply the mass balance that you know, right?
Yes.
Apply mass balance. So the
0.63 divided by 17.
0.63, yeah, yeah, that will be, so the full equation will be 0.65, that is the initial concentration, will be equal to the final concentration into whatever is the capacity, that is 17.6024 into
Yes.
the concentration of activated carbon. Okay,
Yes.
so what is the answer you are
30,
getting?
35.7.
Yeah, 35.7.
Yeah.
So it will be 0.0357 gram per liter, or you will get it as 35.7 milligram per liter. Actually, it is 79, so it will be 35.8. We can write 35.8 milligram per liter. Okay, very simple and direct. Okay, we'll go to the next problem. Yeah, so this is a little bigger problem, but I think on the same lines it is there. So it says that as a result of effluent chlorination, the amount of chloroform formed was found to be 0.12 milligram per liter. Okay. How much powdered activated carbon will be required to treat an effluent flow rate of 4000 meter cube per day to reduce the chloroform concentration to 0.05 milligram per liter? The friendly adsorption isotherm coefficient for chloroform are Kf is equal to 2.6 and 1 by n is equal to 0.73. Okay, I hope you understood the problem. So same Here the pollutant is chloroform, and the initial and final concentrations are again given, but here the absorption coefficients are given. Okay, so we have to apply it and then calculate the answer.
Sir, is it 0.95
0.95 watt
kg per day?
kg per day. 0.95.
Uh,
uh, I think in kg per day it will be more, right? I think you are almost correct, but you have to multiply by 1000.
Again multiply by 1000.
I think you have not multiplied. Have you multiplied?
Sir, I just calculated Q is equal to
Okay, so
2.6.
everything is in. Uh, have you changed to liters to meter cube? That
Yes.
thing. Okay. I think somewhere something is going wrong here. So there will be two. One is one time you have to change the liter to meter cube. So multiply by 1000 and then divide by 1000 again for kg. So
Uh,
two are there. So effectively nothing is there. So both the effectively nothing you have to do.
mhm.
Okay. Okay. Let's see. So here I will just take a different approach because
Okay.
we have seen this approach of solving the problem. So here again another approach is there. So generally how we define the absorption capacity. So absorption capacity QE, we define it as the volume by mass into the initial concentration minus the final concentration. Okay, so this is how we define the absorption capacity, right? And one more way of absorption capacity, we will say it as x by m. Okay, and that we define in terms of the isotherms, that is kf into c to the power 1 by n.
1 by n.
1 by n. So these are the two ways. Okay,
Hmm.
so
Hmm.
if we equate, so from 1 and 2 we will be getting v by m is nothing but kf c to the power 1 by n divided by c naught minus c. That thing will go there. So c naught minus c. So now here we know everything. So kf is 2.6 into 0.05 to the power 1 by n, that is 0.073 divided by 0.12 minus 0.05. So we will get the v by n something around 4.17 liters per gram. Okay, this is what we will get. So once we get V by M, we can calculate M by V, that is nothing but 1 by 4.71. So it will be around 0.24 gram per liter. Okay, just this will change. So once we get the mass per volume, so the amount of required, okay, activated carbon will be required, will be nothing but 0.24 gram per liter into 4000 meter cube per day. So this meter cube I will change to liter. So 10 to power 3 liter per meter cube. And I will also change this gram to kg. So 1000 kg, 1000 gram per kg. Okay. So if you solve everything, you will get 960 kilogram per day. Okay. Directly we can get it. So this
Ah,
is
yes, sir. 960.
960. Yeah.
Yes, yes.
Okay.
I just got same, but I've just calculated it kg per day.
Yeah. So that's how you just have to find it in kg per day. Okay. So same, like this is another approach to solve the problem. One more previous approach we have seen there. So this is another one. Okay. I hope you are able to understand all these things. No, not. Okay. Okay. We'll see the next question. So though it looks a bit longer problem, but many things are asked. So this is a complete design of a filter, carbon filter. Okay, so a fixed bed activated carbon absorber has a fast mass transfer rate, and the mass transfer zone is essentially a sharp wavefront. So just they are describing about the carbon absorption. Okay, so assuming that the following data apply, determine the carbon requirements to treat a flow rate of 1000 liter per minute and the corresponding bed life. Okay, so bed life also we have to find out. So the compound is TCE, that is the trichloroethylene. Initial concentration is 1, final concentration is 0.005 milligram per liter. GAC density is 450 gram per liter. The capacity factor, friendly capacity factor KF is 228, and the intensity parameter 1 by n is 0.62, and the EBCT, that is the empty bed contact time. Empty bed contact time is 10 minutes. Okay, and they are telling to ignore any kind of biological activity that is happening within the column. Okay, so so again, biological activity, if it is happening, then some kind of degradation will happen, which we are not accounting for. So it's like you have to find out the complete design. So for the complete design, we need how much of carbon will be required, what is the volume of water that is being treated, and what will be my bed life. Okay, so these three things have to be answered. So first, I think you can start with the mass of carbon required. Okay, try to solve the mass of carbon required, and then we will see how to get the other things, that is the volume of the treated water and the bed life. Okay, I'll wait for 2 minutes, just try it out, let's see what happens, then we will discuss the solution. Okay, let's see how to solve this problem. Hmm, or I should wait for him to return. Stephen, are you there?
Sir,
Yeah, hello.
sir,
Yeah, please go on.
I have no idea, sir, for this question.
Okay, this question. Do you have like the previous question? Did you follow?
No, sir, I just joined 5 minutes earlier, I think. That's it.
Okay. Like I will explain you a bit about these problems, these
It's,
kind of problems. Okay, so basically, these are all kind of what we say batch study problem. So the last one with what we did. So this is not regarding this 25th problem.
yes, sir.
So these are the batch study. So what happens in batch studies that we have a reactor or anything, a beaker or so a reactor. So in that, suppose some solution is there, it is having any kind of contaminant. Okay, so let the contaminant be toluene. Okay, some toluene kind of contaminant is there. So initial concentration will be known. So suppose initial concentration is some 10 milligram per liter. Okay, now to
Okay, sir.
to remove this toluene out of the system, what we will do, we will add some activated carbon. We are adding some activated carbon into the system. So what we want is, while we are mixing it properly and some other specific environmental conditions when we are maintaining, what will happen, this toluene will get absorbed on this activated carbon, it will get absorbed, and from the water it will get attached to the activated carbon. And with time, let's say after time t is equal to some 10 hours, okay, the final
Okay, sir.
concentration is around 1 milligram per liter. So
Mm.
that means this 9 milligram per liter has been is
Removed.
going into the activated carbon. So our main aim is to find out the dose of this activated carbon. The
Oh,
dose of this activated carbon, how to get it. So basically, most of the time, some particular isotherm or some particular equation it will follow. Okay, so these, like if it is following a friendly isotherm or that equation, okay, so it says that the capacity, the absorption capacity Q, which is in milligram per gram, okay, it is equal to some constant kf into the final concentration to some power. Okay, so these two are constant. These things is based on the adsorbent and whatever isotherm it is following, so kf and c by n. So in question, generally this equation is given to you. Okay, so in
okay,
the
sir.
last problem, the kf value was, I think,
Let's
around
see.
73.4. Okay, one question 73.4, and this 1 by n was given as 0.365. Okay, so suppose in I will solve like one of the previous problem. So there the initial concentration of the pollutant or toluene was given as 0.65, and then the final concentration was given as 0.02. So these are all in milligram per liter,
Okay,
right?
sir.
And yeah, and the isotherm was given as Q as 73.4 into C to the power 0.365. So this was the question. So from here, you have to find out what is my dose of activated carbon. So for what first we will do, we will first find out what is my adsorption capacity Q. So my capacity Q will be equal to 73.4 into CE. C is the final effluent, so 0.02 to the power 0.365. So it will be around something, it will turn out to be 17.6024. Okay,
Okay.
17.6024. Now once we get the, so what is happening, initially some pollutant was there in the system, right? After that, some lesser pollutant is there in the system, plus whatever pollutant is absorbed over the activated carbon. Okay, so if you add, so if we compare the initial quantity of pollutant with the final quantity of pollutant, the mass balance can be done. So we will apply the mass balance. So applying mass balance, so what it says that whatever initial concentration C naught will be equal to the final concentration plus whatever is absorbed. So whatever is absorbed is nothing but Q, that is the absorption capacity, into the concentration of activated carbon. So that's how we will do the mass balance. Okay,
Okay, sir.
this is the
Okay.
C naught, this is C, this is Q into CAC.
Huh.
So initial was 0.65, finally 0.02 plus 17.6024 into CAC. So CAC will be getting it as 0.03579 gram per liter, or I can say CAC is equal to 35.8 milligram per liter. So that's how you will get the dose.
Okay, sir.
Okay, I hope it is clear now.
Yes, sir.
Right? So now instead of having a batch reactor, suppose uh, some kind of column is there. Okay, some kind of column is there. It is filled with some activated carbon, and some influent is coming and effluent is coming out from here. Okay, so all the contaminants will be getting absorbed throughout the length of this activated carbon. Okay, so that kind of problem was the previous one which I was going to discuss. Okay, so here
Okay, sir.
let's say the compound is some trichloroethylene. Okay, initial concentration
Right.
is given 1, final concentration is given also. Then the density of the activated carbon is given because I want to calculate the mass. In the last problem we calculated the dose, that is in milligram per liter. Now I want to calculate the mass, so that's why they have
Okay.
given the density, and then the friendly, what is the kf term, n by n term, what everything is given. And apart from that we can also calculate that how much of bed life is there, like this much of carbon if I am putting, suppose some 100 kgs I am putting, so what, how many days it will run, what is the bed life. So for that we need some time. Okay, so empty bed contact time is given as 10 minutes. So all the equations are given. So now you have to design. So for designing any activated carbon system, you should know what is the mass of activated carbon you need, what is the volume of water it can treat, and what is the bed life. So these are the three things which are generally required for the design of any activated carbon system. Okay, so again we will see how to solve this problem.
Uh,
Okay, so this is question
Okay.
number 25. So first you have to find out what is the usage rate. So the granular activated carbon usage rate, like how much mass is getting used per time or per liter, we have to find out. So is estimated by, so whatever the mass of GSE divided by the discharge into time. Okay, discharge into time we will be getting as, it will be equal to the initial concentration minus the final concentration divided by the QE, that is the uh,
Yes.
absorption coefficient I told you. So C naught minus CE, it will be equal to KF CE to the power n. So that's how we defined earlier. So initial concentration is 1 milligram per liter, final concentration is 0.00005 milligram per liter, KF is around 228, and then C is 1 milligram per liter to the power 0.62. Okay, so if you solve it, you will get out 0.036 gram of GSE will be required per liter. Okay, so now to find out the mass, because we need the mass of carbon, so the mass of carbon required for, I told you, for some time, like how much mass is required for 10 minutes of EBCT. That is the empty bed contact time. So EBCT is empty bed contact time. So this mass will be equal to the volume into the density. Volume into the density will give me the mass. So what is volume? Volume is nothing but time into discharge. So time here is nothing but the EBCT into the discharge into the density of GSE. So EBCT is around 10 minutes. Okay, then Q is given as 1000 liter per minute, and then density is 450 gram per liter. So we'll get the carbon required. The mass of carbon required will be equal to 4.5 into 10 to the power 6 grams. So we got the mass. So once we got the mass, we will now calculate the volume of treated water. So now determine the volume of water treated using a 10-minute EBCT. So that will be equal to the mass of GSE for given EBCT. So this is the mass of GSE for the given EBCT divided by the usage rate of GSE. So usage rate also we calculated. This is the usage rate. So this much gram per liter will be used. So 4.5 into 10 to the power 6 gram divided by 0.036 gram per liter. So we will need 1.26 into 10 to the power 8 liters. So this much of volume of water will be treated. Okay, so volume also we got. So this is the first thing. This is the second thing. Volume also we got. And at last we have to find the bed life. So what will be my bed life? So my bed life will be equal to the volume of water treated divided by the discharge. So this will be equal to 1.26 into 10 to the power 8 liters divided by what is the discharge? Discharge is 1000 liter per minute. Okay, and I want to convert everything into days. So it will be 1440 minute per day, because in minutes it will be too high. So the final answer will be 87.5 days. So this is the third thing. So bed life, volume, and mass. So these three things are required for the design.
Deadly.
So these things are mentioned here. Okay, so again a problem, though it looks a very big problem, but within 2 lines we can solve it. So it says that again a treated wastewater with a flow rate of 1000 liter per minute is to be treated with PAC, okay, packed activated carbon, to reduce the concentration of the organics measured at TOC from 5 to 1 milligram per liter. So initial concentration is 5 milligram per liter, final concentration is 1 milligram per liter.
1 milligram per liter.
Yeah. The Freundlich isotherm parameters are developed as discussed previously, assuming the flow, the following data applied, determine the PAC requirements to treat the wastewater flow If PAC costs $0.5 per kg, estimate the annual cost of the treatment, assuming PAC will not be regenerated. So here we have to find out the cost. First, how much of PAC will be required, the dosage, and then the cost. So two things are required. And same, initial final density is given, KF, 1 by n, everything is given. Okay. So just go through the question once again. I will wait for a minute or two for you to understand, and then I will discuss the solution.
Okay, sir.
Just wait for a minute. Okay, let's see how to solve this problem. So again, similar approach we will do. So for question number 26, similar approach, we know that m by v is nothing but c naught minus c divided by kf, c 1 to the power n. Okay, so this will be nothing but 5 minus 1, kf is 151 to the power 0.5. So if we solve this, we will get m by v is equal to 0.0267 gram per liter. So we got the dose. Okay, so once we got the dose, so directly we can calculate the annual cost. So the annual cost for PAC treatment will be equal to, so first the dose, that is 0.267 gram per liter into the flow rate, that is 1000 liter per minute. This minute I will convert into days, so 1440 minute per day, and days, so for 1 year we have to find out, so it is 365 days per year. Again, the whatever the cost, so it is $0.5 per kg, and to convert everything into kg we will do 1000 gram per kg. So very simple, in one line we can do. So first, what is the dose into the so dose into the flow, then time conversion into annually how much, how many days,
Per year.
the cost,
Cost.
everything. So just multiply everything, we will get the answer as, in dollars you will get definitely, so 7008 per liter. So this much of money you have to spend for the treatment, very direct.
Okay, sir.
Okay, I think these many numericals were only there. So we will quickly discuss the leftover MCQs where whatever is there. So
Okay,
I
sir.
think, yeah, from here, from question number 11. So it says that activation of carbonized materials involves exposure to steam, pyrolysis, formation of pores and fissures, all of the above. So what do you think activation means in for carbonized materials like the activated carbon? What does activation mean?
This is activation. The formation of pores and fishes, sir.
Yeah, formation of pores and fissures is correct. Any other thing?
And pyrolysis means
What do you mean by pyrolysis?
pyrolysis.
You might have heard about it, right?
Yes, sir.
So pyrolysis is generally we use while we want to make the carbonized material. Okay, for the
Oh,
formation. So it happens
formation.
in the absence of oxygen. Okay, increasing the
That's
temperature in the absence of oxygen. It's a kind of thermal treatment in the absence of oxygen. So in that way, some biomass or something will be converting into some carbonized material. Okay, so
oh,
that's a
pyrolysis.
formation process, not activation process. So in activation, we generally expose it to steam. Okay, so
Steam.
with the exposure of this steam, we will increase the surface area. So by surface area, I mean it will increase in the number of pores and fissures. So by
Mm,
activation, we mean to say exposures to steam or the
mm.
formation of pores and fissures.
Pores and fishes.
Okay, so this is the correct.
Okay, sir.
So this is called as carbonation. No, this is known as activation, and
Mm,
carbonation is the process of pyrolysis. It is called carbonation or the
Uh,
formation.
it is-
Okay, so two are
okay,
different
sir.
things. One is carbonation, one is activation.
Okay, sir.
Now next, which of the following statements are correct? Granular activated carbon is heterogeneous media for adsorption. Only natural and not synthetic organics can be removed by GAC. More hydrophilic a compound is, the higher tendency to get absorbed to GAC. Polar compounds are typically not removed by adsorption by GAC. So it is talking about adsorption of GAC. Okay. So
Yes,
which
sir.
of the following statements do you think is correct? Just go through it one by one and then tell me.
Sorry, sir. Actually, I couldn't watch your videos. So
Okay.
that's why I have no idea. Better you will explain, sir.
Okay. I will do. I will do. So you know that activated carbon is used for adsorption, right? So this
Okay, sir.
activated carbon is generally, I will directly come to the answer. So this is having a very complex kind of structure. There will be many pores of various different sizes. Okay, and there will be many functional groups attached to the this activated carbon. So these functional groups only will help us to get the contaminant adsorbed onto it. Okay, it will get attached, it will form some chemical bonds. Okay, there will be so many pores. Okay, so since it has so much of complexity and a porous structure, it is generally heterogeneous in nature. It is not homogeneous, it is heterogeneous. Okay, nothing is
Okay, sir.
uniform, it will be a heterogeneous kind of structure. So
Mm,
first option is correct. Then
okay, sir.
coming to the next problem, only natural and not synthetic. So it is
Mm,
saying that only natural things will be absorbed, but that is not the case. Even synthetic things, if there is a proper molecular size, if it has a proper polarity, then definitely they also will get removed. So statement A
mm,
is incorrect.
it's false, sir.
Okay, it falls. Both natural and synthetic, based on the characteristics, can get absorbed.
Can be removed.
Yeah. Then it is talking about hydrophilicity. So whenever a compound is hydrophilic, so hydrophilic means hydro means water and philic means a tendency to like or liking. Okay. So hydrophilic means water liking. Okay.
Okay, sir.
So if a compound is hydrophilic, then it will stay in water only. It will not get absorbed to GAC. Okay. So more the hydrophilicity, lesser will be the absorption capacity.
Uh,
Okay. Are you
okay.
understanding my point? I see
Ye-
there is a pollutant.
Yes, sir. Yes,
Either
sir.
it will be
Yes,
in
sir.
water or it will getting absorbed. So the more hydrophilic it will be more water living and it will be staying in water only. Okay, so
Yes, sir.
statement 3 is incorrect.
Mm.
Okay, so for
Okay.
it get to be absorbed, it should be more hydrophobic. Phobia means fear. Okay,
Mm.
so the more it is water fearing, it will be better for us for getting absorbed. And then
Okay.
the last thing is uh, whether polar compounds or non-polar compounds. So generally these non-polar compounds are hydrophobic. So that's why non-polar hydrophobic compounds are generally attached to the GSE, and polar compounds which are mostly hydrophilic are not removed by GSE.
Okay.
Okay, so you understood all the points about
Yes, sir. Yes, sir.
GSE? Yeah. So
Yes, sir.
that's what. Now next,
Mm.
reverse osmosis or RO membrane fouling occurs due to chemical scaling. Is it true or false? What do you think?
This fouling occurs due to chemical scaling.
Yeah. You know about fouling,
No.
right?
Yes, sir. Fouling.
Fouling means some kind of deposition will happen on the membrane due to its
Mm.
due to that fouling.
Chemicals.
The water will not
No,
be able
sir.
to.
Only bio things only involving in this reverse osmosis, I think.
No, that is not always true. Okay, so it can be a bioscaling, it can be an organic scaling, it can be an inorganic scaling.
Chemical scaling
Chemical
also.
scaling can
Oh,
also happen. So that
okay, sir.
so in that way it is a true statement.
True. Mm.
Next. So here we have given two types of absorption. One is physical absorption and one is chemical absorption.
Chemical absorption.
So you have to tell me what are its specific, what are its characteristics. Okay, some 6 statements are given on the right side. So you try to read it and tell me which one are for physical.
Physical.
What do you think is good for physical?
Mm. It's- So absorption is a new topic to me, sir.
No,
That's why I have no
just
idea.
think about it. Suppose in one thing some physical reaction is
Physical
happening.
absorption.
Okay, physical
Non-space.
absorption or physical reaction is happening, and in one
Okay.
thing some chemical reaction is happening.
Mm.
Okay, so what do you think? Physical, okay, let's talk about which will be reversible. What do you think will be reversible? Physical processes or chemical processes?
Reversible.
Physical means some kind of attractive forces or some kind of van der Waals forces are there. Okay,
Yes, sir. Mm.
and chemical means it will form some kind of bondings, some proper
Okay.
electron exchange bondings. So what do you think
Mm-mm.
will be reversible easily?
Mm-mm.
Chemical bondings are reversible or physical forces are reversible?
Physical.
I am saying chemical bondings are reversible or physical forces are reversible. Which one you think will be reversible type?
Physical, sir.
Physical, yeah, definitely. So that means physical adsorption will be reversible. One more
Okay,
thing,
sir.
okay. Then you
Mm.
see specific exchange of electrons. So if electron,
Chemical.
so
It's
chemical, so
chemical
that is
absorption.
chemical
Mm.
adsorption. Then chemical will be non-reversible, right?
Yes, sir.
And physical absorption is very common. Physical forces
Uh,
attraction will be happening, so it's a common type of absorption. So if we see,
Absorption. Yes.
for
Mm.
physical A, D and E are correct. For chemical
Mm.
B, C and F are correct. So
Okay, sir.
physical adsorption is non-specific, so it can come
Mm.
and bind anywhere based on the
Mm.
pores or based on its specificity. It can
Mm.
come and bind anywhere. Then it is
Mm.
reversible and it is
Mm.
commonly used. And then
Yes, sir.
chemical adsorption, there is exchange of electrons. It is non-reversible because electron transfer will happen and chemical bonds will happen. So it is non-reversible and it is rarely used in water treatment.
Okay, sir. Okay, sir.
Okay, so like that we can define. Next problem. I think, is it visible to you? The small
Slightly,
diagrams.
sir.
It's not visible, right? Okay, so
And
we'll just skip this problem. It is not maybe when I share the PPT, you can just zoom in and just see. Answer is given. Okay,
okay, sir.
answer is given. You just go through it. You will understand.
Mm,
It's very simple problem. Nothing there.
mm.
Nothing is there. Okay, next problem. The correct sequence for attraction to a typical ion exchange resin for calcium, magnesium, and strontium will be Sr2 plus, Ca2 plus, Mg2 plus. Okay.
Okay, sir.
Then affinity of ion exchange material is higher for ions with smaller hydrated radius. So we have to
Smaller.
select the correct option. Okay, so suppose three ions are there: calcium, magnesium, and strontium. Okay,
Mm.
so
Uh,
what will be the affinity for ion exchange resin? Will it be more for strontium? Okay, so that's what is given. And then the next statement is saying that affinity will be higher for ions of smaller hydrated radius.
explanation of it.
So are the both statements are correct or incorrect? What do you think?
Sir, calcium.
So first you should know whether strontium has a higher hydrated radius or lower hydrated radius. Okay, so here the correct answer is C, that is both the options are correct because strontium has the smallest hydrated radius followed by calcium, then magnesium. Okay, so
Magnesium is higher. Mm-mm.
yeah, highest hydrated radius. So that's
Okay.
why the affinity is more for strontium than calcium than magnesium. So
So
the
both
second,
statements are
sorry,
both statements are correct answer.
yeah, both statements are correct, and B
Mm.
is the explanation for one. Okay, so
Oh,
B
okay.
statement is the explanation for the A statement. So like that you
Okay,
can.
sir.
This question we have already solved in the example, so no need to go
Yes,
through
sir.
this one. This also we have solved. Okay, this one we have to see which of these options are correctly matched. Okay,
Okay, sir.
so dislike of water is hydrophobicity. Van der Waals
Yes.
forces is surface charge.
Wonder was
Electrostatic
okay.
force is physical attraction. Chemical force is pi and hydrogen bonding. So what do you
Mm.
think? Which is correctly paired here?
Dislike of water based on the hydrophobicity, I
Yeah,
think.
just now we discussed. So dislike of
Yes, sir.
water is hydrophobicity. Any other
Mm.
thing is correct?
The chemical forces bonding, hydrogen
Yes,
bonding.
yes. So chemical forces is pi and hydrogen bonding.
Okay,
Okay,
sir.
so A and D are
Okay.
correct. So you know this one. So and these van der Waals forces are weak physical attractions. Okay, so generally
Mm.
surface charge we will say are electrostatic forces, not van der Waals forces. So that's why it is
Okay.
incorrect. And then the
Okay.
second one, electrostatic forces are not typically physical forces. We will say electrostatic forces is forces between some oppositely charged species. So plus and minus, if it is getting attracted or uh, repelled, so those are the electrostatic forces. So that's why those two options are incorrect.
Okay, sir.
Okay, next one. Oh, answer I've already shown. Okay, anyway, we will discuss. So again, this is regarding the ion exchange. So we are saying that weak acid resins have lower pKa value compared to the strong acid resins. Then it is easier to regenerate a weak acid than a strong acid resin. There is a stronger attraction to singly charged ions due to smaller hydrated radius. And then in a resin column, the ion exchange begin to saturate the upper levels before the lower levels. Okay, given
Okay.
that the direction is from top to bottom. So do you have any idea about these things?
The answer is shown, sir. B and
Answer
D.
is told. Okay, so generally, suppose a weak acid is there, so the pKa value will be more. Okay, for
Yes.
strong
Yes.
acid, pKa value will be less. So option A is
Mm.
incorrect. Then
Mm.
it is easier to generate the weak acid. That is true. Okay,
Mm.
then strong
Mm.
acid. And D option is correct because if the flow is from top to bottom, okay, then
Mm.
upper levels will be saturated first, then the lower levels. So option D is also correct.
B and D.
Okay, B and D are correct. Okay. Select the particles which are specifically removed by nanofiltration, but not by the filtration of higher filtration. Okay, so nano, we have different types of filtration, right? One is micro, then ultra, then nano, and reverse osmosis. So
Okay.
what does nanofiltration removes? Is it algae, protozoa, or bacteria? Is it some small colloids? Is it some divalent ions or organic matter, or some monovalent species? What do you think will be removed by only nanofiltration, not by something else?
Mhm. Small colloids, sir.
No, it's not the correct answer, because colloidal particles can be removed by ultrafiltration.
Oh,
Okay,
yes. Mm.
so generally this nanofiltration will remove the divalent or dissolved organic matter. Okay,
Divalent ions and dissolved
yeah.
organic
See,
matters.
algae, protozoa, bacteria will be removed by both microfiltration and ultrafiltration. Okay, because they are bigger in size. Small colloids, though smaller in size, will be mostly removed by ultrafiltration. Then divalent ions or dissolved matters. Okay, these will be
Oh,
removed by the nanofiltration. And then monovalent species like small ions of sodium, like monovalent species, they will not be removed by any of these three things. They can be only removed by the maybe the reverse osmosis.
okay, sir.
Okay,
Algae, sir. The first one, algae protozoa,
that is removed by micro or ultrafiltration.
micro.
If it
Colloids
is
is for
virus,
ultra.
if it is virus, then it will go to nano or reverse osmosis range.
Okay,
Okay,
sir.
and also in algae, protozoa, and bacteria, there are various classes. Okay,
Sir,
not
which one
all.
is the best, sir?
Sorry.
Ultra and
See, the highest pore
micro,
size
macro.
is first is macro. So bigger
Okay,
particles are removed by macro. Then little
okay,
smaller
sir.
is ultra. Then little
Okay, sir.
smaller is nano. Then the
Mm.
last one is the reverse osmosis. So like
Okay,
that,
sir.
like it goes.
Okay, sir. Micro, macro, ultra, nano.
Okay. Next one. Select the ways in which both iron and manganese removal can be done. Okay, we are talking about removal of iron and manganese. So what do you think among them can remove both iron and manganese?
Iron and manganese removal can be done.
Can it be
Let's see.
removed by lime soda method?
Iron and manganese.
Yes, right. It can be removed by
Yes.
lime soda method,
Uh,
but the pH should be more than 9.5. If it is less than
more than.
9.5, it will
Uh,
not be getting precipitated. Okay. Then
okay,
again,
sir.
chemical oxidation also we can use. If we can
Uh,
oxidize this
uh,
ferrous and manganese 2 plus 3 or plus 4 forms and then get it precipitated. Okay.
okay, sir.
And then the
Okay, sir.
last one is sequestration. Sequestration, we will add some polyphosphates molecules and it will getting attached to that. So it can be removed by sequestration. So these are
Okay,
the
sir.
three methods. Okay. I think that's all. So these numericals we have already discussed. Okay. So
Okay,
yeah, I think that's all for today.
okay, sir.
Okay, so again we will have class day after tomorrow. So it's an extra class, though we have classes only on Tuesdays generally. But this is
Okay,
an
sir.
extra class we will have day after tomorrow from 5 to 7 p.m. Okay,
Okay, sir.
Thursday
Okay, sir.
5 to 7 p.m. So please try to attend that.
Attend, sir. Yeah, definitely I will try to attend, sir.
Okay, so you are getting benefited from these lectures, right?
Sure, sir.
Okay,
100%.
yeah.
Uh, uh,
So if you have any feedback, you can fill up the feedback form you will be getting through NPTEL. Okay, so
yeah,
whenever you feel like
okay, sir.
any improvements,
Okay,
you
sir.
can tell us.
Yeah, definitely, sir. It's improve our knowledge, and also in case if it is having any interested area, in the sense we will study through the NPTEL only,
Okay. So
whether it is relevant to us or not.
you are student or you are working
Yeah, yeah, I'm faculty.
faculty. Okay. So
Uh,
thank you.
Thank you, sir. Thank you, sir.
Okay.
Thank you so
If you
much.
don't have any questions, you can leave the session. That's all from my side.
Okay, sir. Thank you, sir.
Okay. Thank you. Bye.